Hello everyone. So, welcome to class 32 where we will continue our discussion on thermodynamic potentials that I just briefly started in the last class and how properties emerge out of these thermodynamic potentials. So, in the last class we just to give you a recap. So, we were looking at so what I mean, so there is a cause and an effect, there is an intensive property and an extensive property, and typically some of them are conjugate properties, right. So what are the properties that relate between these conjugate properties? The CPs, the stiffness, the compliance which relates between stress and strain, stress being the intensive property, strain being the effect which is an extensive property, or the other way around, strain being the cause and stress being the effect, right. So what relates stress and strain? Then if I so look at the electrical domain, then I have electric field and displacement, but not just that, we have also looked at cross coupling, right. So if I apply electric field, do I create any sort of strain in the system? That is the converse piezoelectric material effect, right. So intensive property in one domain, in the electrical domain, coupled to an extensive property in another coupled to an extensive effect in another domain, right. So strain, for example, is extensive in mechanical domain, whereas electric field is the intensive property in the electrical domain, right. So what couples that? These cross coupling properties are piezoelectric properties, for example, piezocaloric properties, for example, heat of deformation, right, or the other way around. So intensive property in one domain coupled to an intensive property in another domain, or an extensive property in one domain coupled to an extensive property in another domain. We wrote this big triangle and then we said all these properties, right, so emerge out of such an analysis, and all these properties fundamentally are equilibrium properties, right. And what is an equilibrium property? We sort of gave this understanding, so from an energy perspective, these are properties where energy is stored, right. So in the material, electrical energy is stored in the material, and how much is it stored? So if you know the susceptibility, or if you know the dielectric constant of the material, you can understand how much electrical energy is storable or is stored in the material, right. So upon the application of an electric field. Similarly, I can view this as also in terms of forces, right. So in our spring mass system, that's the best example, right. So where the K or the spring constant, right, so tells me if I pull the spring to a certain extent, so what will be the restoring force on this spring, right. So how much is the restoring force? That is determined by your spring property, which is K, and so extending this to other thermodynamic properties, what I am saying is there is an underlying thermodynamic potential, just like the potential energy or potential of the spring mass system, and then the curvature of the double derivative of that potential function as a function of the cause that you apply should give me a property, right, so of interest. So just like spring constant, right, that can be applicable in thermal domain, that can be applicable in mechanical domain, that can be applicable in the electrical domain. That's sort of the discussion, and then we started moving on to what is a thermodynamic, first law, second law of thermodynamics. We just brushed through it, and then we looked at what are the potentials that come out of first law and second law. So one of the potentials is du, right, so that I wrote here this one, right. So now I am sort of volume normalizing this energy, and du is a potential, but so what does this equation mean? Du equal to Tds plus x dx plus E dd, right. So this means so by writing the equation in such a differential form, what I am saying is how can I change the internal energy of a system? U is the internal energy. If that is the question, then the answer is, right, so it is dependent on so by changing either S or x or small x, sorry, or d, right, so or the charge, right, or a combination of them. That is the ds. ds means I change the entropy, dx means I change the strain, dd means it is a change in the displacement, right. So or the charge on the capacitor, right. So, here my cause or the independent variables are typically S, so the entropy, right, X which is the strain, D which is the displacement, right. So, these are all in some sense these are all extensive quantities. So, ideally to directly say that okay, so I am changing the the electrostatic internal energy of the system, the experiment that I should do to change electrostatic internal energy of the system is to take a parallel plate capacitor, right. So, I am taking a parallel plate capacitor with a dielectric in between, and to change the electrostatic energy what I have to do is I have to first I need to have control on the charge that I can place on the capacitor, not voltage, right, place on the capacitor, right. So, I have to be able to put some charge on the capacitor, right. So, plus 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 here and minus 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 here, right. So, I have to be able to put charge on the capacitor. So, my control variable is charge, not voltage, right. So, not electric field, right. How do I put charge? I can have a current source, I can charge the capacitor up, right. So, typically it is current or charge that is the control variable. Control variable is charge or the cause is charge, not voltage. You are generating voltage by applying charge, right, but the cause itself is charge. Okay. So, you are generating electric field by applying voltage, but the by applying charge, but the cause is charge, right. Now, you may argue that what is the difference, what is the big deal, right. So, whether I apply charge and measure voltage or whether I apply voltage and measure charge, I should measure the same properties. That is not necessarily true. We said in nonlinear devices, so if you go back to our first few lectures, there I said applying current and measuring voltage and applying voltage and measuring current in a device that is nonlinear or in a device that can be hysteretic, in a device that there can be lot of things happening is not necessarily one and the same, right. So, you get different answers depending on what is the cause, what is the effect, right. So, let us distinguish it. In a linear system it may turn out to be one and the same, but so in a nonlinear system it is not. Okay. So, also so we if you go back and look at our Hall effect so discussion, I specifically made it a point not to call the thing that we were measuring, the transverse conductivity we are measuring is not Hall conductivity, because I am applying current and measuring voltage. So, what I measure is Hall resistivity, right. So, there is a difference, right. So, I measure rho 1 2 and all the analysis that I did, if you go back and check your notes, it is actually to look at rho 1 2, not sigma 1 2, right. So, there is a difference, especially since these are tensorial quantities, and when you go into so the correct way of doing is, if you are applying current and measuring voltage, you are measuring resistance. If you are applying voltage and measuring current, you are measuring the conductance, right. Similarly, here if I am applying charge and measuring voltage, right. So, that is the experiment to change the internal energy of my capacitor or of my dielectric material. Okay. So that is what this says. The equation du equal to TdS minus x dx minus E dd tells me that I have to change the charge, or I have to strain the material, or I have to supply heat to the material, right. So, to change its internal energy, right. So, but I cannot increase the temperature. Temperature is a dependent variable now, because I am heating the material, the temperature increases. Temperature is the effect, S is the cause. Okay. So, the causes are all here. Okay. Now, it is not always so the easiest experiment I can do is not to put charge in a controllable fashion, right. So we looked at ferroelectric materials, right. So, in ferroelectric materials there is a spontaneous polarization, right. So, I apply voltage in this direction, let us say, right. So, when I apply voltage in this direction, so I am applying an electric field, when I apply voltage in this direction, I am applying an electric field in this direction, right. So, when this is the electric field, this is the polarization, this is the voltage. and then the polarization suddenly flips, right. So, at certain electric field the polarization flips, right. So, at E greater than E c the polarization flips. When the polarization flips, there is going to be a huge current or huge charge that is uncontrollable, right. So, through the external circuit, because the current so far there is very minimal capacitive current. So, before E less than E c, right. So, the way I do this experiment, let me actually tell you that, right. So, I apply a voltage ramp like this, right. So, this is voltage as a function of temperature as a function of time, and then I am measuring the current as a function of time, right. So, in a ferroelectric device. Okay. So, now if it is just a capacitor, if it is not a ferroelectric material, right. So, since I am applying voltage as a function of time, the current I measure I will just be C dV by dt, right. So, capacitor times dV by dt. So, I should be something which is a constant, right. So, if it is a simple capacitor, I can apply a ramping voltage or I can apply a constant current. I can apply a current source and just provide constant current to the capacitor, that is okay. I am always charging the capacitor, right. So, once the capacitor plate is charged, I should make sure that I am removing charge at a constant rate to the external circuit, right. So, I can charge control capacitor, that is okay, right. But let us say I have a ferroelectric material. So, in a ferroelectric material, as I keep on applying voltage, right, as I keep on ramping up the voltage, so initially the polarization is in a certain direction. Let us say the polarization is it turns out that the polarization is in down direction, right, and then it has to switch to polarization which is in an up direction, right. So, at some electric field, at some voltage V, at this voltage, right. If it is switching to an up direction, right, there is a sudden flip of polarization which is in this direction to this direction, and that sudden flip of polarization, that is, there is a sudden change in the charge on the capacitor, right. Now, the capacitor, the parallel plate of the capacitor has positive charge, right. So, initially, and this has negative charge, and there is a polarization which is it is the other way around. So, let us say it has a negative charge. So, this discussion we did it a bit earlier. I have negative charge here and I have positive charge here, which means that the polarization is pointing up, right. Now, let me just reconfirm. Okay. So, let us do it properly. So, if I have a capacitor where polarization is pointing up, on this terminal I have negative charges, on this metal because I have positive bound charges, they have to be screened by negative negative free charges, these are free charges, and here I have here I have positive free charges, right. So, free charges I am just going to color it in this fashion, right. These are the bound charges. The bound charges are going to be like in green color, right. So, these are bound charges, right. Then I need to apply an electric field in the opposite direction, right. So, if I need to apply an electric field in this direction, I have to, for me to switch the polarization, I have to apply a voltage which is in this fashion, right. So, if voltage electric field goes from positive to negative, right. So, these are, so I am actually putting positive charges on this plate and negative charges on this plate because of application of voltage, which means the electric field is in this direction. This is the direction of electric field, right. So, when I apply an electric field in that direction at a critical electric field, the up polarization transforms to down polarization, which means so now all of a sudden, right, I have negative charges on my plate here, right. So, all of a sudden there is a delta p, right. So, in a very short interval of time delta t, right. So, delta p is nothing but 2 p r, right. So, by delta t, and delta t is very short. So, I have a huge current in a very short interval of time, right. So, that huge current will be shown like this as a current peak, right. So, there is a huge the charges on the plate flip from negative to positive. So, there is a huge change in current, and that current huge change in current is given as this peak here. Okay. Similarly, so when I am increasing voltage on the negative side, I will have a peak on this side, right. So, as a result, if I plot the current versus voltage, the current versus voltage will look something like this, right. So, initially current is increasing, voltage is increasing with time, there is a peak in current, then voltage is decreasing with time and the current is negative, but so on the negative side I have another peak which goes like this and then it goes this way, right. So, this is the positive coercive voltage and this is the there is a peak there, right. So, I do not have the page. So, there is a negative coercive voltage here minus V c. Okay. Anyway, so and then if I start so I have I versus V which is like this. I have to draw it again, right. So, this is the experiment I am doing, and if I integrate, if I plot I dt which is nothing but charge versus V, so initially the current is just constant and negative. So, if I start from here, initially current is constant, which means my charge will increase with voltage, that is okay, but suddenly there is a huge switch. So, the charge is going to so there is going to be a discontinuity here, it is going to increase like this, then again it is going to be something small but with a constant slope, then again I am coming this way, right. So, if I am coming this way, I have the same constant slope, right. So, I am reducing the voltage and suddenly again there is another peak, which means the current goes down like this, right, or the charge actually goes down, or I am putting in negative charge onto the plate. So, the charge actually goes down this way and then again it is a constant, and so then I come back and then I go back to 0, right. So, that is this portion. Okay. So, what I end up getting is Q versus V, or the so called polarization voltage graphs. Okay. So, loops. Okay. So, it is supposed to be something, a ferroelectric material is supposed to show hysteretic loops like this. Okay. Now, the point is, so this is the experiment, and in this experiment it is difficult to control charge. I can control the field across the ferroelectric capacitor because I can apply a battery and control the field, but so at so especially when the ferroelectric is switching, from P up to P down, there is a huge current or charge motion in the material, and this is this is not something that you can control, right. So, this happens very fast, right. So, it happens in depending on the material in some nanoseconds to speed of sound in the material especially, right. So, this is not very controllable, right. So, if I am doing a charge controlled measurement on ferroelectrics, doing a charge controlled, hence so on ferroelectric materials, doing charge control measurement is hard, but then what is easy is I can do current, I can do voltage control measurements or field control measurements. I can apply an electric field of my just by applying a battery I can apply electric field of my volition. Control measurements are easier to do. Okay. So, as a result so if I say, if you tell me that okay, so du is something like TdS minus sigma dE x dx minus EdD, to control this is hard, right. So, rather what I would say is, okay, so I do not care about changing u per se, but I am going to define another thermodynamic potential phi, which is going to be u plus, oh sorry, this is all plus here. Okay. Did I write any minus anywhere? Let me just check. Yeah, so I did not write minus anywhere, I was just a bit worried that I may have messed up the signs, but okay. So, now I am going to define another thermodynamic potential, which is going to, I am going to call it phi equal to u minus let us say E d. Okay. So, if phi equal to u minus E d, if I look at d phi is actually du minus d E d, which is E d d minus d d, right, and that will be equal to T d s plus x dx minus d d, right. Phi 1, I am going to define it as phi 1 because I am going to define several such thermodynamic potentials. So, this is also in units of energy, it is a potential, right, but it is not really internal energy, this is not internal energy, this is some thermodynamic free energy, right. So, if I subtract E d from u, right, there is some I am subtracting E d because I want to be able to control E, right. So, I am going to call it some free energy, the energy available to me that I can change, right, by changing the magnitude of E, right. So, this is the energy available to me for control, let us put it that way. And what am I controlling here in this experiment? I can control E, right. So, I can control the electric field. By controlling the electric field, I am changing a free energy, a thermodynamic potential, which I call a free energy of the system, right. So, T d s plus x dx minus x dx minus d d e, right. So, here my control variables or the cause are s, x and e. Okay. Now, similarly you may say, okay, but it is, I can control, so it is easy experimentally, it is easy for me to control temperature, right. So, I can apply temperature and put in heat, right, rather than giving heat of a particular value. So, I so giving Q of a particular value, right, rather than controlling the heat input into the system, or rather than controlling the heat input into the system, it is easier to control temperature and let heat be a consequence of temperature. I am putting in heat or removing heat just by controlling the temperature of the system, control temperature of a system, right, because I have some control system that I can fix into a source of heat, right. So, in furnaces, right, so I have a resistive heater or something like that, and this resistive heater, the exact temperature that this resistive heater heats my device to can be controlled through some sort of a control loop, right. So, because of all the technology that I have at hand, I can control the temperature, right. So, I can increase the temperature at will, or I can decrease the temperature at will, and so on and so forth, right. So, so I can control the temperature of the system rather than the Q of the system. Similarly, I can strain the system, but rather than that I can so so I can strain the system, that is okay. I can the strain experiments can be both displacement controlled, strain mechanical experiments can either be displacement controlled or strain controlled or force controlled. Again, using a control loop, I can exactly apply the force, the desired force on the material, right. So, force controlled, which is stress controlled, right. So, so there are certain parameters that I can control in a given experiment, and I need to construct so the idea is I need to construct the free energies or the thermodynamic potentials that are easily so that change by changing the control variables, that change deterministically, right. It is not changing. So the thermodynamic potential is not changing because I apply stress induces strain and then strain changes the thermodynamic potential, right. D epsilon changes the thermodynamic potential. Rather than that, I want this change in my control variable should directly change the thermodynamic potential of choice, right, deterministically and directly with a control variable of choice. Okay. So, like that so then let me define phi 1 I defined as u minus E d, right. Phi 2 I can define as u minus T s minus x x, right. So, then if I look at what is d phi 2 is just du minus T d s minus s d t minus minus E d also, if I can put, minus E d d minus d e d e minus x dx minus x dx, okay. And that is what is du. Du is nothing but TDS plus DDE EDD plus x dx, right. So, minus all these things come here, right. So, I can just write it as minus s dt, right. So, minus x d capital X minus d capital E, right. So, now I have a thermodynamic potential phi 2, but phi 2 will be dependent on changing temperature, changing x which is the stress, and changing the electric field, right. So, I have to change phi 2, right. So, I have to do temperature controlled experiments, either do temperature control. So, in the experiment I need to control the temperature. Temperature is something in my control, right. So, I can change the temperature at will. If I want temperature of 300 degrees, I should be able to set the system at a temperature of 300 degrees Celsius. If I want the temperature at some 250 degrees Celsius, I should be able to set the temperature of at 250 degrees Celsius, right. But if I have to control heat, if I have to put in some 1000 kilojoules of heat, I should be exactly able to put in 1000 kilojoules of heat. That is a difficult experiment to do, right. So, but temperature is easy to change. I have to either do temperature controlled experiment or force controlled experiment, mechanical force controlled experiment. That is how I control stress, or I have to do a voltage controlled experiment electrically, or a combination of all. I can apply stress, I can apply force, I can apply voltage simultaneously, right, and then change the phi 2 of the material, right. So, combination of these three, okay. Then if I can define another potential phi 3 which is dependent on T small x and capital E, right. So, then I just write phi 3 as u minus T s minus E d, right. So, there is no x x there, right. Similarly, I can define phi 4 which is dependent on entropy or the heat, right. You can make various such combinations, right. So, you can define various such thermodynamic potentials, various such thermodynamic potentials, and that depends on what are the accessible control variables. Okay. Now, Okay, so that is about the thermodynamic potential. So, it is not a unique potential, people call, so if you are taking a course on thermodynamics, people call something Gibbs free energy, people call something Helmholtz free energy. If I am able to control the volume of my system, right, and then change the energy that is available to me to change just by controlling the volume is what is called Helmholtz free energy. The energy that is available to change by controlling the pressure and temperature of the system is what is called Gibbs free energy, right. So, in the more sort of growth language, right. So, similarly I can have work done which is electrical, which is also mechanical and magnetic in nature. So, based on all these things I can define several such thermodynamic potentials, right. So, it is not unique to either internal energy or so it depends on what is the energy available to me given that these are my control variables, given that I can control all these variables independently, what is the energy in the system that I am going to change, that I call a free energy, and that free energy potential I just define it mathematically as we did just now. Okay. Now, let us take one of these free energies, right. I am going to say let me take d phi phi 3 probably, or okay, so that is fine. So, phi 3 equal to u minus sigma minus xx, these both are tensors xij minus Ts, right, minus Ed, that is Eidi. Okay. So, that is my thermodynamic potential that I have taken. I think this is phi 3 or phi 2. I think I defined this as phi 2, right. So, let us go back to phi 2. Okay. Now, if I differentiate phi 2 with respect to d. Okay, so what is d phi? I think we also wrote that. D phi is minus s dt, right, minus x dx minus d d. Okay. So, this one I write it as I j, this one also I write it as I j. Okay. So, this is what we have seen earlier. Now, if I take a partial derivative of phi 2 with respect to ei, by keeping so I am not changing temperature, I am not changing the stress, right. So, this is in a constant stress state and this is at a constant temperature. Okay. So, then if phi 2 is supposed to be ideally dependent on temperature, stress and ei, but I am going to fix these two and I am just going to look at how phi 2 is dependent on ei. Okay. So, now phi 2 is dependent on ei as minus di, right. Okay. So, that is the first thing. Then let me take second derivative, right. So, second derivative of phi 2 again with respect to ei, right, keeping all the other temperature this is g I square, keeping temperature and xij constant. So, that will be minus di by dei, and what is that? That is my epsilon ii, or that is my dielectric constant, right. So, this is what am I saying here, or minus the dielectric constant, right. So, what am I saying here? I have a thermodynamic potential which is analogous to my u of the spring mass, right. So, here I am writing the analogy. Okay. So, and then I take a double derivative of the thermodynamic potential, and this can be controlled by a variable. In this case, this thermodynamic potential is controlled by or changeable by a variable ei, right. So, here also it is controlled by displacement of the spring, control meaning if I change the displacement of the spring, the energy of the spring changes, right. And then in that case what am I saying is dou square phi by dou E square, which is the curvature of phi with respect to E, right, Ei. Here I look at curvature of u with respect to x that is my property epsilon, right. Here this is my property, or minus epsilon, right. So, the sign is not very important. Here this is my property which is K, or the spring constant, right. So, this is property which is dielectric constant. So, thermodynamic framework wise, dielectric constant or spring spring constant, these are one and the same, they are double derivatives of some thermodynamic potential, right. I mean they have a similar origin in that sense, right. So, thermodynamic origin is more or less one and the same. Okay. So, we have dielectric constant, which is how in terms of the energy storage, right. So, what is the energy of a capacitor, or the so that is given as half epsilon E square. So, that tells me how much energy is stored in a capacitor, right. So, this is here the energy stored in a spring is half k x square, right. So, k, so this is a property like k, right, and then so just very thermodynamically we said that just like k has an underlying thermodynamic potential which is u, this also has an underlying potential which is the phi 2 that I defined here, right. So, phi 2 has been defined here. Okay. So, now let us do something else, let us actually look at phi 2. So, d phi 2 is minus s dt minus x, sorry, small x d capital X minus d capital E capital D, right, and then I am just going to write I and I here. That means that this is minus d minus dj dj minus and so on and so forth, right. So, minus dk, so all the components, so it is sigma of that essentially. Okay. So, but I am just going to use Einstein notation and use just notation I, so that so over, if it is the same index, I will sum over the index, right. So, Einsteinian tensorial notation I will just use it here. Okay. Okay. Then I am going to do what is dou phi 2 by dou E I. Okay. So, that we said is keeping temperature and x constant, that we said is minus di, fantastic. Now, I am going to say what is dou square phi 2 by dou E I, but instead of doing dou 2 E I, right. So, I am going to say, okay, so or let us put it this way, what is dou phi 2 by dou E I, dou by dou E j, right. So, now I am going to take this derivative second time with respect to another component of electric field, not the I component, but the j component, right. So, now that is going to be minus dou d I by dou E j. Now, what is this? This is nothing but minus epsilon I j, right. Okay, very good. But phi, phi is a thermodynamic potential and an analytic function. Phi 2, I keep forgetting phi 2, but yeah, and this is an analytic function, and mathematically all these analytic functions have a property that say that dou so whether I differentiate it with respect to dou x dou y should be equal to dou square phi by dou y dou x, right. So, whether I differentiate it with respect to y first and x next, or x first and y next, it does not matter, the order of differentiation does not matter. So, this is a property of an analytic function. Now, I can go into details, I can explain what this means physically, but I will leave it for you as self study. You can so I will leave it to you to visualize what does it mean that first of all a function is dependent on two different variables, what is it how is it graphically represented, and then if I change one function first and then the second function, what are the trajectories that I am taking on this graphical manifold, and if I change it, what are the trajectories I am taking. It is not a very trivial statement to make, right. So, but mathematically analytical functions have such a property, right. So, I am not going into the details of the mathematics of this. Okay. So, we will just use it in our case. So, then so I take this equation, I will rename it as equation 1, and then I am going to say dou by dou E j dou phi 2 by dou E I should exactly be the same as dou by dou EI dou phi 2 by dou EJ. Okay. Now, this one I said is minus epsilon ij, right, and this one will be what, dou by dou EI and then this is dj, and that will be minus epsilon minus, there is a minus here, oh sorry, that is minus epsilon ji, right. So, what did we just prove? Epsilon ij equal to epsilon ji. I have been using this fact without really proving it, that my second rank tensor properties are all symmetric, right. So, with respect to the equilibrium properties, here is the proof, right. So, it does not matter, I can take any potential, right. So, I can do the same thing with for example, something like some other second rank tensor. It does not need to be electric field, it can be magnetic field, right. So, any second rank tensor will have an underlying thermodynamic potential. This is equilibrium property, any equilibrium property of second rank tensor will have an underlying thermodynamic potential, and because of this fact, right, because of this fact that this is an analytic function, all I have are these so epsilon 1 2, epsilon 1 3, but this also will be epsilon 1 2, this also will be epsilon 1 3, this is epsilon 2 3, this is epsilon 2 3. So, so symmetry is imposed, symmetry in the second rank tensor is imposed by thermodynamics. Okay. This is valid for equilibrium properties. Now, if you remember, I also used the fact that sigma, which is conductivity, a non-equilibrium property, is also symmetric, is also a symmetric tensor. Or I said sigma ij equal to sigma ji. This I did not prove yet, because this is not an equilibrium property, but I will prove this when I do kinetics, right. So, wait for the next module for me to prove this. Okay. So, with that, let us conclude this lecture. So again, we have developed what thermodynamic potentials are in this lecture, and based on thermodynamic potentials, we have actually mathematically seen that these properties are similar to spring constants. They are double derivatives, or they are curvatures of these thermodynamic potentials with respect to a cause, right. And depending on the control variable, the potential can change, right. So, what is the free energy, that is what the potential determines. And finally, so we did show that all these thermodynamic potentials, especially the second rank thermodynamic potentials, are symmetric in nature. Okay. So, epsilon ij equal to epsilon ji. Now, I will leave you with with what is called with a simple assignment, where you are supposed to show me that Cij KL is the same as CKL Ij. This is a fourth rank stiffness tensor. Okay. With that, let us conclude this class. Okay. So, let us start with this in the next class. All right.